Let's talk about modeling the atmosphere above us for aircraft conceptual design and performance analysis purposes. How useful is the ubiquitous International Standard Atmosphere, or ISA? Its simplicity makes it perfect for back-of-the-envelope hand calculations, but does it still have a place in a computational design world? What are its pitfalls? Are there any alternatives? And finally, how do we build effective atmosphere models in Python in a matter of seconds using, for example, some of the open source tools in the ADRpy library? Let us first look at how well ISA represents the real world. Well, that depends first of all on which element of it is most important to you. If you want to model ambient pressure, it is pretty close. Take a look at this plot of pressure labs with geopotential altitude. The blue curve is what ISA says it should be. The greyish fluff around it represents just over 500 soundings of the atmosphere taken over a period of 12 months over Nottingham in the centre of England. Clearly, pressure varies a bit as weather systems come and go, but not enough to worry us, not from an aircraft engineering point of view anyway, about how representative the International Standard Atmosphere is of the atmosphere, the real atmosphere. Another way of looking at this is to compare the altitude estimated by the GPS unit on board the radio sonde that recorded each of those soundings that make up the fluff with the pressure altitude using the International Standard Atmosphere from readings taken by the barometer of the radio sonde. A bit of noise in the top right corner, deep into the stratosphere, but generally a good agreement. Of course, in most cases, you would do your performance calculations in terms of pressure altitude anyway, in which case even this problem goes away. What about the temperature though? Same location, same time period, same 500 or so weather balloon soundings, and a messier picture. The ISA does get some key things right though. The tropopause, that first turning point, seems to be consistently where the ISA has us expecting it, and the tropospheric temperature lapse rate, the slope of the first straight section, also seems to be on most days around the 6.5 Kelvin per kilometer mark predicted by ISA. This suggests that we could approximate the temperature profile of almost any day at this location simply by offsetting the ISA by a few degrees one way or the other. An ISA minus 15C and an ISA plus 10C in this particular example could clearly be used as reasonable models of the extreme conditions one might encounter when flying over the Midlands. Here is what a Python model of the ISA might look like. A function designed to calculate the temperature in Kelvin according to the International Standard Atmosphere with the altitude range and the desired temperature offset in case of an off-standard ISA as its arguments. Now ISA divides the first 47,000 meters of the atmosphere into 5 layers, and it defines the temperature as a 5-piece, piecewise linear function across these layers. So first you define the base temperature at each of these layers, the altitudes of which you already specified, as well as the appropriate lapse rate, which allows you to create the linear segment for each of these. And then you just check which of these layers you're in, and depending on the answer, you deploy the appropriate slope and intercept to calculate the temperature in that particular layer. You could then construct similar functions for density, pressure, and the speed of sound. But there is an easier way. Namely, you could use ADRpy, which already has all of this implemented in quite an easy-to-use way. First of all, you need some modules from ADRpy, most importantly the atmospheres module. And in case you wanted to do some unit conversions with the results, you will also need the unit conversions module, as well as mtools for ACDC, or miscellaneous tools for aircraft design, which might also come handy when it comes to visualizing the atmospheres. And speaking of visualization, you will also need PyPlot. So how do we build an international standard atmosphere in Python using ADRpy? Well, it is as simple as creating an atmosphere object, which is simply an instance of the atmosphere class stored in the atmospheres module. And once we've created one of these, the argument, if left blank, means that we've created a standard ISA. If you enter a number there, then it will offset the ISA by the desired temperature. Once this object is created, we can access all of its various attributes, including these useful functions that allow us to calculate various parameter variations with altitude. So take the temperature, for example. If I want to know what the temperature is at 1,000 meters according to the ISA, then it is as simple as doing this. If I want something else, for example, the air density at sea level, which is what no argument means, and here it is in kilograms per meter cubed. Now, if you wanted to generate plots of these things, all we have to do is create an axis in meters. Usually these take arguments in meters. And here we created a range from 0 to 50,000 meters. And if we want to plot things in terms of feet, we will also need to convert this axis into feet. And this is where the unit conversions module from ADRpy comes handy. Meters to feet simply does what it says on the tin. It converts this altitude axis into an altitude axis in feet. We can then calculate the temperature, the speed of sound, the air pressure in millibar, and the air density in kilograms per meters cubed using the appropriate attributes of the ISA object that we just created. And then, using from the miscellaneous utilities available in ADRpy, using this panel plot with shared y function, with some fairly intuitive arguments that are described in the documentation, you can generate a nice 4-panel plot of these quantities that we just created, and plot them against the altitude axis in feet. Let's say you want to know what the ISA geopotential altitude corresponding to 2000 Pascal or 20 hectopascal or 20 millibar is in meters. Fortunately, the ISA object we just instantiated from the atmosphere class earlier has a method that allows us to do just this type of calculation. It's one of these methods that begins with an underscore because it's a bit of a secret undocumented feature, but it can be very useful. You just enter 2000 as the argument, and it tells us that the geopotential altitude corresponding to 20 millibar is 26,481 meters. This can be very useful. For example, meteorologists often talk about winds at the, say, 20 millibar level. If you wanted to know what that meant in terms of altitude, this is the function you could use to do that. Now, what if your aircraft is meant to operate worldwide? Is the ISA equally representative everywhere? Due to the approximately oblate spheroid shape of the Earth and various other astronomical and climatological reasons, The answer is no. In fact, it only really works well in the mid-latitude band. Let's have a look at the high-latitude example. Here are 660 radiosonde profiles taken over a period of 12 months over Point Barrow, Alaska. The blue line is once again the isotemperature model, and it is clearly much less representative of this Arctic world. We are at 71 degrees northern latitude than it was of Nottingham. The tropopause is much lower. The temperature starts rising straight away as we enter the lower stratosphere, and the lower troposphere is, as you'd expect, much colder. We're inside the Arctic Circle after all. Moreover, frequent days with low-level temperature inversions, you can clearly see these below 5,000 feet or so, mean that even the sign of the temperature lapse rate is often wrong. Now, offsetting the ISA either way is not very useful here because its baseline zero offset version overestimates temperatures in the troposphere and underestimates them consistently in the stratosphere. The Arctic stratosphere is, perhaps a little counterintuitively, generally warmer than the ISA would have it. The atmosphere above the tropical regions of the planet also presents an issue for the ISA. Consider these 700 or so temperature profiles recorded above Chennai, India, 13 degrees northern latitude. The ISA, the blue line, gets the tropospheric lapse rate roughly right, but pretty much everything else is a long way out. Look how thick the troposphere is above India, and look how cold the stratosphere is, with temperatures dipping below minus 80 Celsius, where the ISA model is only predicting minus 56 Celsius. Another noteworthy feature of the Chennai data is how little seasonal variation there is, especially above 5,000 feet or so, significantly less than in the mid and high latitude cases we saw. Now, all of this has some flight planning and mission simulation implications. Aircraft performance charts of the traditional printed variety are generally presented in terms of ISA offsets. So you'll have figures for ISA conditions, ISA plus 5, ISA minus 5, ISA plus 10, ISA minus 10, etc. Now, if you're planning a flight at mid-latitudes, and based on the air temperature at the departure airport you conclude that conditions are, say, ISA minus 20C, you might be able to get away with calling it an ISA minus 20C day, and using the ISA minus 20 performance curves, not just for takeoff, but also for climb and cruise performance planning, at least for local flights. But clearly, an ISA minus 20C temperature departure in Alaska is absolutely no guarantee, for example, of an ISA minus 20C stratospheric cruise. The ambient temperature up there could well be tens of degrees higher than ISA minus 20. So, how do we account for the possibility of such conditions in our design calculations? Well, an obvious solution is to use ensembles of actual historical atmosphere profiles, such as the balloon soundings we have been looking at here. This approach is a natural fit with Monte Carlo type uncertainty quantification techniques, and we will come back to it another time. Another way of looking at this is to design for the least favorable conditions the aircraft might reasonably encounter in service. There is a US military standard titled Global Climatic Data for Developing Military Products, which contains a good collection of such extreme atmosphere profiles. They are catalogued on the basis of whether they feature unusually high or unusually low values of temperature or density at altitudes of 5, 10 or 20 kilometers. They quantify what unusual means. 1 in 10 percentile values are provided, meaning that on any given day the real world is 1 and 10% likely, respectively, to be more extreme than the specified extreme profile. So let's have a look at one of these profiles. Here is the 1 percentile extreme low temperature at 20 kilometers, just over 65,000 feet, profile in green on top of the Alaska dataset. Clearly a really nice approximation of the lower extremes of the temperature ensembles, up to the tropopause anyway. It even knows that these sorts of conditions are often accompanied by an inversion at low levels. So far we've used the atmosphere class to create international standard atmospheres, but it is capable of more than that. If we look at the class header, we will see that it also admits a profile argument. If we specify a profile, it will create an atmosphere featuring a specific profile or a specific variation of the physical properties of the atmosphere across the altitude spectrum. This could be based on a balloon sounding, or we could get one of the profiles out of the Extreme Atmospheres handbook we just talked about. So, how do we get one of those extreme atmosphere profiles? Well, ADRpy has a method for that as well, and it's called Military Handbook 310. And we just have to tell it which of the atmospheres available we want. So, for example, we want the low temperature at 5 kilometers atmosphere, and this will return two observation profile type, OBS profile type variables, each containing an observation profile across the atmosphere. The first, the 1 percentile atmosphere, and the second corresponding to the 10 percentile atmosphere. So if we store these in some suitable variables, let's say military %1, military %10, we can put one of these into the atmosphere class to create an appropriate atmosphere. So for example, if I put military 1 percentile profile in here, and we instantiate the class into an object called very cold atmosphere. From this point onwards, this atmosphere object behaves in exactly the same way as the ice has behaved that we created earlier. So we can just call any number of functions associated with it, and it will tell us, for example, what the temperature is, let's say at sea level in the, or actually let's go with 5,000 meters, which is where this gives us the extreme coldest conditions, the low temperature at 5 kilometer atmosphere. And there we are, minus 52.65 Celsius. Similarly, we can query any number of other attributes. For example, if we want to find out the density at sea level, for example, in this atmosphere, we will find that it's a rather momentous 1.6 kilograms per meter cubed. Yes. A good starting point for further information might be the ADRpy repository on GitHub, where in docs, ADRpy notebox, you will find a notebook describing all of the methods and functions and concepts we talked about today. Alternatively, you can also go to the project documentation, which once again offers a lot of detail, including examples explaining the use of all of the functions and methods we talked about in this video. Thanks for watching this quick primer on engineering models of the atmosphere. We will discuss design, performance and uncertainty quantification implications of all this another time. Meanwhile, happy coding and happy designing.